Thank you for having me here. So I will talk today about ISS, of course, but in the context of time delay systems. And I will give you an overview of some Lyapunov results in this setup, and also raise some open questions which I believe would deserve some more interest. So before starting, before starting, I would like to mention that most of the things I will discuss today are taken from this survey paper that we published last year with Karafyllis, Pier Domenico Pepe, and Wang in MCSS at the occasion of Eduardo Sontag's 70th birthday. And so you'll find, hello, Eduardo. So you will find, of course, much more details in that survey. It's like 50 pages long, but if you have some courage and some will to read it, you'll find everything you want in there. Okay, so let me start. This is the outline of my talk. I will briefly introduce what is a time delay system and some fundamental properties of such a system. I will then talk about input-free systems before moving to ISS and integral ISS, and make some brief remarks of conclusion and perspective about this topic. So let me start with what is a time delay system. So a time delay system is a functional differential equation of this form: x dot of t equals f of xt u of t. So u of t is the input, just like in the finite dimensional ISS theory. It's considered as a measurable, locally essentially bounded signal that takes value in Rm. What the main difference with the finite dimensional theory is this xt here, because in order to integrate such a functional differential equation, you need an initial state which is not just a point of Rn, but an entire segment of initial conditions. You see this x0 in red here is a full segment, a full history defined between 0 and minus theta, where theta is the largest delay that is involved in the dynamics. So you need all this knowledge, and once you know this initial state, the applied input, and the vector field f, you can integrate the solution of this system, and you get this blue line. But the actual state of such a system is not simply x at time t, which is a point of Rn, but really the history segment in red here, which is indicated by xt. Okay, so it encompasses all the value of x of t, but over the interval t minus theta t. Okay, so for this, the associated state space is no longer Rn, but it's the set of all such segments, so meaning the set of all continuous functions that go from minus theta 0 to Rn, which I will now call x. Okay, that's the state space of our system. And I will also need two different norms: the norm of the pointwise solutions of x of t. This is a vector, so I will use simple bars to indicate the classical Euclidean norm. But when dealing with the history function xt, I will need to take the soup of a signal over its interval of definition. So I get this double bar norm xt, which is the soup over the considered interval of x of t. Okay, feel free to interrupt me if something is not clear. Would be nice to have some interaction. Okay, so this is a time delay system, and the basic assumption I will make, and that is made in most works in this field, is that the vector field f is Lipschitz unbounded set. So for whatever bounded set of x times Rm, you assume that f has a Lipschitz constant, and also that it has an equilibrium at the origin, meaning f of 0, 0 equals to 0. Under this basic assumption, you have already some interesting properties for free. You have the existence of a unique solution over some interval 0 t max, where t max is surely positive, but can go up to infinity. So at least for little y, the solution exists, and it is unique, okay? And if this interval of existence is bounded, meaning t max is bounded, then for sure the solution gets unbounded on 0 t max. So it explodes when it stops existing, essentially. You also have continuous dependency in the initial state and in the input over any compact interval of the domain of existence 0 t max. What I mean by that is that if you make a small variation of x0 and a small variation on the input signal u, then for whatever bounded interval of 0 t max, you would have a small variation on the corresponding solution. Okay. And you have also some continuous dependency in time. So of course, x of t per se is a solution of the functional differential equation. So yeah, by definition, it is an absolutely continuous function, but also the mapping from t to xt is also continuous on its interval of definition. And if you happen to pick the initial state, not only continuous, but actually continuously differentiable, then you can show that the corresponding map t maps to xt is actually locally absolutely continuous on its interval of existence. So this is useful when you have to study the property induced by a Lyapunov functional, because in order to invoke comparison lemma, you usually have the need for this kind of absolute continuity, and this can easily be ensured by considering continuously differentiable initial states. And the fact of considering continuously differentiable initial state is not a big deal from the generality, because using a density argument, you can show that most stability properties also hold for all continuous initial states when it holds on C1. Okay, so these are classical results taken from these textbooks by Helen Lunel and Kolmanovsky and Mishkis. You can also see the paper by Piero Pepe in 2007, who started to extend the ISS framework to time delay systems. So let me talk about forward completeness now. So forward completeness is exactly the same as in finite dimension. I would say that the system is forward complete if all its solutions exist over R plus, starting from any initial state and from any input u. Okay, so just existence of all solutions at all forward time. A more demanding, apparently more demanding assumption is the bounded reachability set property. It requires not only that the system is forward complete, but that the set you can attain starting from a bounded set of initial state is bounded over any interval, over any bounded interval. So in mathematical terms, it's this: given any t and r, if x0 and u are below r, then for sure I will remain in some ball of radius delta for all the solutions that are produced from this range of initial states and input, provided that I work on a bounded time interval. Okay, so this is the diagram that you can have. I'm starting from a ball of radius r, and I can only reach a bounded set if I work on a bounded time interval. Okay. So in finite dimension, there is this result by Lin, Sontag, and Wang in '96 that says that if you have forward completeness, then you have the bounded reachability set property. And this was actually a crucial result for a lot of stability results and converse theorems. We also know that in infinite dimension, in general infinite dimension, this is not true. There are counterexamples, for instance, the one proposed by André and Fabian Wirtz in 2018, showing that you can have a system which is forward complete, yet do not have the bounded reachable set property. Okay. But since these time delay systems hold a bit in between finite dimension and general infinite dimension, I would say, I mean, it has a very specific structure. I believe it's worth of interest to ask this first open question, whether for time delay systems, once you have forward completeness, you also have the bounded reachable set property. So we have worked on this question. So far, it's still open, but we have preliminary results, particularly with Jason Karafyllis, Pierdomenico Pepe, and Yuan Wang in this paper here in SIAM, showing that if you work on Holder or Sobolev spaces, meaning you restrict the set of initial state to Holder or Sobolev spaces, specific ones, then you do have this implication that forward completeness implies this BRS when measured through these Holder or Sobolev norms. Okay, but the question is still open for the considered state space X that we are considering here. So once again, I believe that this open question is important because it's a crucial ingredient for converse theorem and solutions-based characterization. So I believe it's worth more exploration.
Sorry, can I ask you a question? I mean, you would think that Sobolev spaces are pretty good for applications. I mean, why do you? I mean, is there, from a practical point of view, is there a reason to go to continuous functions?
Well, there's
continuous functions, right?
Yeah, there's a historical reason, I would say, because most of the theory has been developed in this setup. But okay, this doesn't answer your question. The other question is, generality. I mean, how can you predict how in which state a time delay system will be? Whether it will have such a Holder or Sobolev property, I'm not sure. So I don't know. For the sake of generality, I think it's better to work on the continuous state space. But also from practical concerns. Yeah,
because you would think you're talking about the initial conditions, right? And
yeah, absolutely.
You know, most of the time, presumably, you could on a finite interval, right? So you could assume that they're fairly, derivatives are integrable, etc. I mean, there should be a lot of. So
I fully agree with you. I mean, what this result by Yason mostly on Holder and Sobolev spaces, I think it's really of a practical interest. The only thing is that it's not fully in line with the existing theory. Okay.
Yeah. Okay. No, it's a beautiful result. Yeah. Great.
May I intervene, Antoine?
Yeah. Sure.
And Eduardo, if you work on Sobolev or Helder spaces, then you lose continuity of the solution with respect to time.
Oh,
which is a crucial element.
I see, because they're equivalence classes of functions, basically. Is that the thing?
Exactly.
So there's no pointwise. I see. Okay, thank you.
Yes.
Okay. Thank you, Yason.
Okay. Thanks, Yason.
Okay, maybe let one more comment that we could actually also go in the other direction, not making the initial state better, like Herder or Sobolev, but make it worse, like L-infinity space, and many things may become better also in that.
It's true. So these are recent results from our conversation, but not published yet, and I've not mentioned them. You're right. Yeah, so that's an interesting message. I mean, it works for more conservative state space and more general state spaces, but it doesn't work for the state space that was used so far to develop the theory. That's the point. Okay, so anyway, there are some ways to ensure this bounded reachable set property in practice, and I want to mention this Lyapunov-based result. So it requires a function v that is Lipschitz on bounded sets, and that is sandwiched between, on the left, the current norm of the solution, so x of t, a pointwise value, and on the right by the full state supremum norm, possibly with a positive term. We don't care so much. We don't require v to be 0 at 0 in particular, okay? So you take such a function, you differentiate it along the system solution. So here I mean in the Dini derivative sense, okay? But I'm not going too much into details, but and you require any of these two properties. The first one is very reminiscent, for those who have this in mind, of the Lyapunov characterization by Eduardo and David Angeli, because this is equivalent to having forward completeness in finite dimension. So what you require is that v dot, I mean, up to the input term, v dot explodes at most exponentially with respect to time. So that means that v exists at all time, and so the solution exists at all time. That's the reason, okay? But you can require something else, which I think is more useful in practice sometimes, is you require that v is bounded by something proportional to a function of the full history norm. So when you make the computation, it's often easier to get a sup norm of xt, because that's what is involved in your dynamics, rather than recasting everything in terms of the Lyapunov-Krasovsky functional. So this is handier in practice, but the price to pay is that this function alpha underline has to be the same one as the lower bound on v. So it means that you cannot allow for a large k-infinity function here. It has to be the same one as the lower bound on v. But if you do have this, then you have the bounded reachable set property. Okay, so maybe let me illustrate this on this is very a toy example, but to tell you the truth is how I came to time delay system. I had some neuroscience applications, and I got and some delays are involved due to axonal transmission, and that's how I got interested in the theory of time delay systems. But anyway, it's a very basic model of the evolution of the firing rate of a neuronal population. So x of t is the number of spikes per second that are emitted by the neuronal population at some time t. And you have a nonlinear function s, which is globally Lipschitz, and I call L the Lipschitz constant, and it has to be 0 at 0. So think of this model as recentered at 0 around an equilibrium point. And you see that here, the influence of x is through a delayed version of it, because the neurons, as I said, have a finite transmission delay due to the axonal propagation. And so the time it takes for the activity of the population to influence itself is through a time delay theta, okay? And u here is an input signal that represents, for instance, the influence from other brain structures that are not modeled. So if I want to assess a bounded reachable set property for this system, I simply take a Lyapunov functional, which is actually a function. You see that it depends only on the current value of the state, x of t squared over 2. And of course, the sandwich condition can easily be established. You get alpha underline is s squared over 2, alpha bar s squared over 2, and you don't even need the c bar constant. Then I differentiate this along the solution. So I take the gradient of this function, which is x of t, and I multiply it by the vector field, and I get this. I make some basic manipulation, and I end up with 3L over 2 xt squared plus L over 2 u of t. So I recognize exactly the same property as before. What is interesting is that here, you see, I do not make appear the Lyapunov functional, but really the sup norm of the solution. But since it behaves as a squared, which is exactly the form of my lower bound on the Lyapunov function, I can conclude with the previous theorem that the system has the bounded reachable state property without expressing everything in terms of Lyapunov-Krasovsky terms. Okay, it's just to illustrate the purpose. So let me move to input-free system. So for this, I need two ingredients. I will call the LKF for Lyapunov-Krasovsky functional candidates, any function that are Lipschitz unbounded sets and that are sandwiched in this way, meaning lower bounded by x of t and upper bounded by xt. Okay, so I insist that we do not have the same norm on left and right, because usually you cannot get a x of t norm on the right. You will see, for example, that most of the time you cannot get a bound on x of t. And also it's very demanding to have a lower bound involving xt for a lot of practically relevant Lyapunov functionals. So I think it's very convenient to just impose these two different bounds. But when you do impose that you have the norm of xt on the left too, then we call it coercive, because now v of xt is sandwiched between two functions of the norm of xt. Okay.
Sorry,
so,
quick question, just a stupid question though. Lipschitz means exactly what? We have the sup norm in x.
Yeah. So I take f. So if I take a single variable, I take any bounded set of x, and I want that for all xt yt in this set x, f of xt minus f of yt is below L of sup norm of xt minus yt for some constant L.
Right. I was just worried about the metric in x. So it's
on the right is the sup norm. On the left is the Euclidean norm, because it's just a vector field.
Right. So it's just with respect to the sup norm in x. So if you change the topology, like you were worried about, this other spaces, then the function may not be Lipschitz anymore, for example. Is that correct, or am I missing? Like if you take a LP space or something, then it would be the same function would not be Lipschitz anymore. Well, the restriction of the function will not be Lipschitz anymore, right? Maybe.
Yeah.
Okay. I just wanted to clarify that. Okay.
So keep in mind, coercive means lower and upper bounded by xt, but the general sense is lower bounded just by x of t. Okay. Global asymptotic stability is defined as, so I consider first input-free system, so there is no input here, and I consider this gas property as a combination of stability, which is really the stability in the Lyapunov sense. Given any epsilon, I can find some delta such that if my initial state is in the ball of radius delta, then I remain in the ball of radius epsilon at all times. So really the Lyapunov stability, okay? But of course, here I'm using the sup norm everywhere because I'm working in this X space. And I also require global attractivity of the origin, meaning that for whatever initial state, I will eventually converge to the origin, okay? So this is really similar to the finite dimensional gas property. But I can require a little more, meaning U gas, uniform gas, in which case I still require stability in the Lyapunov sense, but now I require uniform global attractivity. Not only I converge to zero, but the rate at which I converge to zero is uniform over bounded sets of initial states. So namely, for any epsilon r positive, I can find a time t, such that if I start in the ball of radius r, I will reach and remain in the ball of radius epsilon in time t at most. Okay? So there is some uniformity here that is not captured in here, because here I'm just saying that I'm converging, but I don't know at which speed, okay? And what is cool with this U gas formulation is that it is equivalent to this natural KL estimate of the solution, meaning that x of t is bounded by a KL function of x0 and t, and which is very handy for converse results, for instance, okay? So in finite dimension, we know that when you have global asymptotic stability, it is necessarily uniform. The uniformity comes for free. Open question 2, is it true also for time delay systems? So that would be nice because this U-gas property, unlike the gas property, imposes no arbitrary large transient overshoot and no arbitrary slow convergence. So that would be nice from a practical point of view. And this second open question, as it says, it's still open, but we have a preliminary result in the same paper as before, mainly by Hassan, which is that if in addition to gas, I impose the bounded reachable state property that I told you about, then I get U-gas, okay? So now the question, of course, is this open question 2 would be solved if we manage to show that open question 1, meaning that forward completeness implies BRS, because gas implies forward completeness, right? So if you manage to show this open question 1, you will also solve open question 2 with a positive answer. And here again, using the same reasoning as before, if you restrict your state space to Sobolev or Holder spaces, you can show that indeed gas implies U-gas, but we still don't know about the set X that we are considering here. All right. So how to ensure this U-gas property in practice? Well, there is this multiple Lyapunov characterization that I can show you. So it's equivalent to requiring that the system is U-gas and to require that you have a Lyapunov-Krasovsky functional and alpha positive definite, PD is positive definite, such that V dot dissipates pointwisely. What I mean by pointwisely is that the dissipation rate involves only the current value of the state, meaning x of t only, not the past value, not the functional itself, just x of t. So this is very handy in practice because when you make derivation on some practical system, you usually end up with negative terms only involving the current value of the state, and it's harder to involve more terms sometimes. But what is nice also is that once you have this, when you have U-gas, you also be sure that there is this coercive Lyapunov-Krasovsky functional and alpha now of class K infinity that dissipates in terms of the whole history norm. So this is very powerful from a further robustness analysis, but would be very hard to get starting from a classical Lyapunov-Krasovsky functional. So it's mostly used as a converse part, this part, okay? This is also equivalent to requiring that there exists a coercive Lyapunov-Krasovsky functional that dissipates LKF-wise, meaning that the dissipation rates involve the Lyapunov functional itself, V. And finally, this is probably, this is more our contribution. It's the same as requiring that you have this KL dissipation, meaning a negative term, which is a KL term of the current solution and the history norm. So you see that it's very similar to this pointwise dissipation, but it's even weaker in the sense that this dissipation rate can be very small when xt gets large, because xt can be very large as compared to x of t. So this last characterization is especially useful when you use Lyapunov functionals of the form a logarithm of 1 plus v. In that case, when you differentiate, you have 1 over 1 plus v appearing everywhere. And that brings you these bad terms xt here in the reasoning. So it's good to know that you can still deal with these bad terms without compromising global asymptotic stability. Now I move to global exponential stability. So no big surprise, xt bounded by k x0 exponential minus lambda t. And the difference with gas is that now the convergence is at an exponential rate, but also that the transient overshoot is at most linear in the initial state, okay? And I also make the notion of LKF a bit stronger by requiring quadratic bound rather than generic K infinity function. So a guess LKF will be I bound by a quadratic term of x of t on the left, of xt on the right. And coercive guess LKF is the same, but with the norm of xt on both left and right. Okay. Based on this, I have this characterization of global exponential stability. Having guess is the same as having an LKF-wise dissipation for a guess LKF, meaning v dot smaller than minus a constant time v itself, or to have a coercive LKF that dissipates in terms of the whole history norm, meaning minus a xt squared. Okay, and you can find these results in the papers by Pier Domenico and Yasson or Hiabaidar in 2022. But what's missing in this statement is the pointwise characterization that we had for global asymptotic stability. In other words, my question is, assume that you have a guess LKF, so sandwiched between two quadratic functions, and now you impose only a dissipation quadratic, but only in terms of the current value of the solution. Do you still have global exponential stability? Well, the question is also open. I think it would be very nice to solve it because it's, as I said, much handier in practice to get just x of t in dissipation rate. And also it will be coherent with the global asymptotic stability theory, for which a pointwise dissipation is indeed enough. And one consequence of a result I will show you after is that this is indeed true when you focus on local exponential stability, meaning that if you require this only on a ball around the origin, then this pointwise dissipation does ensure local exponential stability. And since it also ensures global asymptotic stability, if you require it everywhere, then you can have gas and local exponential stability. There is a paper by Pierdomenico and Di Fernando in 2021 about this. Okay, so what result do we have in this direction? We have this this result with the same team, so Yuan, Pierdomenico, and Jason, which require V dot. So I get a guess LKF, so sandwich between quadratic functions, which satisfies V dot smaller than minus a x of t squared, and possibly even a positive term involving the whole history norm. So this is rather surprising because if you look at this dissipation rate here, V dot is not even required to be negative because xt can be much larger than x of t. Just take a particular state for which x of t equals 0 and xt is equal to 1, then of course V dot has no guarantee to be negative here. Okay, but you assume this. So in the case where you consider epsilon equals 0, you're exactly in the setup of the open question I just raised, meaning a pointwise dissipation rate. Okay, but I assume more here. I assume that I can find a positive positive definite symmetric matrix P and a constant C, so that one of these two conditions hold. Meaning that, so what are these conditions? In both cases, I compute x of t transpose PF. So this is just the evolution of the norm induced by P along the solution of my system, if you want. So this condition imposes me that this quantity does not explode too quickly, whereas the second condition that it does not decay too quickly. Okay, so I have an upper and a lower bound. Well, if any of these two conditions hold, then for sure there exists a positive epsilon bar such that if my epsilon here remains between 0 and epsilon bar, I have global exponential stability. Okay, so for free, I have some tiny robustness with some respect to some additional term, even though I'm dissipating only in terms of x of t. So these are gross restrictions that partially solve this open question 3. You just pick epsilon equals 0 and you have a partial answer to this open question. An important point to notice is that any of these two conditions trivially holds when f is globally Lipschitz. Okay, so at least for globally Lipschitz systems, once you have a pointwise dissipation, you have global exponential stability. And in the paper, we provided explicit estimate of this epsilon bar, the maximum epsilon you can tolerate, but okay, as often with Lyapunov techniques, it's, I think, a very, very conservative value of epsilon bar, but at least it exists. All right, so let's try to see how it applies to the previous example of neuronal population. So I have no input here. So when there is no input, I boils down to this system. And I take this as a Lyapunov function. So V of xt is just a non-delayed value, quadratic non-delayed value, plus the integral over the delay interval of a quadratic function of the state. Okay, so here you see that why the two different bounds in the bounds in the sandwich are very important, because on the left, you can difficultly have something better than x of t. And on the right, there is no hope to get x of t because of this integral term. So you really need to have two different norms. So anyway, the sandwich condition that I require is easy to get. I get underline a equals 1/2 and overline a equals 1/2 plus theta. But what is more interesting is when I differentiate this function. So this term is easy to differentiate. I take the gradient of this x of t, I multiply by the vector field. And differentiating this, well, I differentiate an integral. So it's just x of t, because I have t here, x of t squared, minus x of t minus theta squared, which I get here. I rearrange the terms a little bit, and I get negativity both in x of t squared and in x of t minus theta squared. So I have a bit more than pointwise because I also have a negative term in the delayed values, but there is no hope for this Lyapunov function to get a dissipation term that would involve the whole V, simply because nothing shows up in forms of this integral term here in this expression. Okay, so LKF-wise dissipation would not work to conclude global exponential stability. But still, we can conclude, because since I assume that S is globally Lipschitz, my whole vector field is globally Lipschitz. So I fall in the case where having a pointwise dissipation rate is enough. And indeed, I conclude that I have global exponential stability if this term is positive, meaning L is smaller than 2. So L, remember, is the slope of my nonlinear function S here. All right, so let me move to ISS. So ISS, here again, no big surprise. It's really exactly the original definition by Eduardo. The only difference are the norms, of course, because I need to take the soup norm everywhere on X0 and on XT. And just like in finite dimension, it has very interesting property because it not only induces global asymptotic stability for the input-free system, but also a small steady state error for small inputs, a bounded input, bounded state property. And also when the input U converges to 0, you're sure that the state will eventually converge to 0 too. Okay, I think I don't need to convince you of the power of ISS here, but was worth mentioning. So for ISS of time delay system, I have this following characterization in Lyapunov-Krasovsky terms. It's the same to require that the system is ISS as requiring an LKF-wise dissipation. So alpha is of class K infinity function, gamma as well. But what is important is that I need to dissipate in terms of V itself. Okay, so if I manage to have a dissipation in terms of V, I can conclude ISS. And once I have this, I am sure that there exists a coercive LKF V that dissipates now in terms of the whole history norm, so a more demanding requirement. And also this is equivalent to having an implication form. So here it's on the right, it's a pointwise dissipation, but which is required whenever V is greater than the input modulo this function chi, right? So in order to estimate this, you most of the time has to express everything in terms of V. And so it's just an apparently pointwise dissipation, but in truth, it's you need to express everything in terms of V. Okay, so look at this reference to have more details about this characterization. But what you can notice, what is missing here in this characterization is once again, this pointwise dissipation, meaning what happens if I dissipate only in terms of my current solution's value? Is the system ISS? So this is a question that has obsessed me for more than 5 years now. I have bothered a lot of you guys about this question, but it's still unsolved. So I believe it would be very interesting to solve it because it's much handier in practice. I'm currently working with Andri and Fabian on this topic, but also with Jason, Pierre Domenico, a lot of people. And here again, it would be much more coherent with the input-free case. And by the way, for delay-free dynamics, this question is totally irrelevant because having a pointwise dissipation, I mean, an X dissipation is the same as having a V dissipation in finite dimensions, simply because V is sandwiched between two functions of X here, which we lose for time delay system. So it's been years that I'm struggling on this question. We have some preliminary results, but still no positive or negative question on this matter. So any suggestion would be more than welcome. But anyway, we do have some elements of response. First one, it was actually the subject of some discussion with Miroslav Kristic at my last seminar 2 years ago. It was about what is called the exponential trick. So let me tell you what is the exponential trick. I consider a particular class of Lyapunov-Krasovsky functional, a non-delayed term here, depending only on x of t, and just the integral of v2 of x of tau. Okay, so consider only the specific class. So it's very useful in practice. A lot of problems can be solved with such a Lyapunov-Krasovsky functional, but it's of course not a full generality. So I require that this Lyapunov-Krasovsky functional dissipates pointwisely. You see that here I'm involving only the current value of the state plus gamma of u. But the key point is that my dissipation rate has to be the same as what the term inside the integral here, modulo a constant term a. Okay, so if I have this, then the exponential trick works. What is the exponential trick? It consists at taking this Lyapunov function and by tuning it a little bit by putting an exponential term here, this exponential term in blue, and possibly a constant in front. Okay, but what is important is this exponential term here. So for me, it was just a mathematical trick. For Miroslav Kristic, it has some physical meaning, this exponential trick. But my point is that it's indeed useful in a lot of... Yes?
This exponential trick exists for many years.
I know.
Standard too.
I know that it exists. I'm not claiming.
2 years ago or something else. This is very standard thing.
Yeah, I know. I'm not claiming that I'm at the origin of this exponential trick. I'm just saying that it's a very classical trick to get LKF-wise dissipation. That's all. But the discussion with Miroslav is whether this has a physical meaning or it was just a mathematical trick to find such a good dissipation. Right? Yes. And let me just show you an example why I believe it's still not a systematic trick. So this trick, at least this theorem, just shows that for a Y class of system, this trick systematically works, okay? But this is an example, so maybe not the most elegant example, but still, it's a scalar system which has an input and some weird delayed terms, nonlinear delayed terms. You can show that the system is ISS by using a Razumikin technique that I will say a word about later on. But more importantly, if you take this Lyapunov function, which is x of t to the 4 and the integral of x of t to the 4, then you get indeed a pointwise dissipation, okay? But if you apply this exponential trick to this function, then there is no way you can get an ISS Lyapunov-Krasovsky function. Actually, this functional here, whatever p and c that you pick, it admits positive value for w dot. So this shows that at least the exponential trick is far from being systematic, even when focusing on this class of integral Lyapunov-Krasovsky functionals. Okay. So going back to this neuro example, okay, I'm taking this Lyapunov-Krasovsky functional, the same as before, and I'm making the usual computation to get a pointwise dissipation here, also a negative term in t minus theta, and a term in u, okay? So I can estimate the dissipation rate is just a constant time s squared, and the input rate is constant time s squared as well. Here again, there is no hope to get LKF-wise dissipation simply because this integral term does not show up. But we are in the situation where the ISS trick does work because the negative term we get here is proportional to the term that is under the integral here. So no doubt you can tune this Lyapunov-Krasovsky functional by putting an exponential here and conclude ISS. Okay. So I have said a word about Razumikin. Let me come back to this result. It's a very interesting alternative to Lyapunov-Krasovsky approach. And I believe that it's not as general as Lyapunov-Krasovsky approach, but it has the interest of involving mostly finite-dimensional theory, because it works with a function, not a functional. You see that V takes value in Rn, not in X. So I assume that V is a Lyapunov function, essentially, and that I have an ISS dissipation whenever V is greater than some function of the all possible values it reaches in the elapsed delay time. Okay, so if V is great as compared to the past values, I require an ISS dissipation. That's what he says. And if I have that this function rho that is involved here that quantifies how much big must be V in order for this to hold, if rho is smaller than the identity everywhere, then the Lyapunov-Razumikin approach tells me that the system is ISS. So this has been formalized by Thiel in the ISS context and also by Yasson, Pierre Domenico, and Zhongping in 2008. So another result we have on this topic is the fact that when you have such a Razumikin assumption, you can actually build a coercive Lyapunov-Krasovsky functional for free almost. Let me be more precise. I assume that I have the above Razumikin condition, and I assume slightly more. In the above result, I require that rho of S was smaller than S everywhere. Here I require that the sup of rho of S over S is smaller than 1. So I cannot stick to 1 to S. I need some distance respect to S. But okay, I think the difference is moderate. Anyway, in that case, under the Razumikin condition, if I take W as the functional defined as the max of 1 over L to the tau over theta V of X tau, this happens to be a coercive ISS Lyapunov-Krasovsky functional that dissipates with a history-wise. So the best you can hope for, essentially. So this result has just been submitted with my PhD student Epifan Loco and Yasson. And it shows a systematic way to, a bridge at least, between Razumikin and Krasovsky approaches. And I believe it can be of interest to have such an explicit Lyapunov-Krasovsky functional to derive some further stability analysis. Okay, I want to mention also Allan approach. So here I give the nonlinear version of Allan inequality given by Pepe last year, actually a recent result. It requires that my function, here again, it's a function, doesn't have, that's the strength of Allan. It works with function rather than functionals. When I differentiate, I need a negativity in terms of all v, plus a positive term involving the maximum value reached by v over the past interval, plus a term in u. Then if alpha dominates this row, in the sense that alpha minus rho is of class k infinity, the system is ISS. Okay, so maybe some people are surprised that I call this a Allan inequality, but if you take u equals 0 and alpha and rho as linear function, then you get really the original Allan result, v dot smaller than minus av plus rho max of v, which is really the linear version of this. So this is just a nonlinear extension of this original Allan result. And here again, we can build an explicit Lyapunov-Krasovsky functional under a slightly more demanding function. Here on the previous result, we required alpha minus rho to be k infinity. Now I need to find a q greater than 1, as close as I want from 1, so that alpha of s minus rho q of s is of class k infinity function, so slightly more demanding than Allan. But still, when I have this, I have an explicit construction of Lyapunov-Krasovsky function that dissipates. It's coercive and it dissipates in terms of the whole history norm. So these constructions, they rely on the following interesting result that I want to mention, which is due to Yason and Zhongping in their book in 2010, which tell you that if you give me a function which is C1 and a constant C which is positive, and you define a functional V as the max of this W over the past interval exponential C tau, then this functional has very nice properties. Most of the time, well, it's not very mathematically rigorous, but whenever W is smaller than V, it dissipates in an exponential way. And whenever, the worst case, W is equal to V, then you have anyway this bound. So this bound is not so good because you have W dot, and W dot is the derivative of a function along the solution of time delay system. So W dot can be positive, okay? But still, this happens only when W is equal to V. And when W is equal to V, it means that x of t, is very similar to xt. So this is something that you can actually use in the study of this term here to show that it's not that bad. Okay, so this is very, very nice result according to me in Yason's book. And I used it a lot of time to solve some questions. Okay, so if I go back to the toy example, I will not go into the details, but I take a Lyapunov function, which is really the classical one. I make some manipulation and I get a negative term in V, a positive term in the past values of V, and a positive term in U. So if I try to apply Allan, this is my function alpha, 4 minus epsilon times S. This is my function rho, 2L times S. And I need that alpha of S minus rho of QS to be of class K infinity function, so for some Q greater than 1. And I can check that this is possible if my slope, the slope of my nonlinearity here is smaller than 2. So I get ISS. And the same, Razumikin is almost the same. If I assume that V is greater than some constant rho 0 and times the max of its past values, then I get only a negative term here, provided that this quantity here is positive. This gives me this condition on rho 0, that it has to be greater than 2L over 4 minus epsilon, but it also has to be smaller than 1 in order to fit the Razumikin hypothesis. And this is made possible if here again, the slope of this nonlinear function here is below 2. Okay, how much time do I have? Yeah, we'll go quickly on the integral ISS part. So integral ISS part is really similar to ISS, but I'm not measuring anymore the impact of the input magnitude, but rather of the input energy as measured through some function delta 2. So this can be seen as a measure of the energy fed in the system by the input U. So really here again, direct extension of integral ISS in the Sontag setup. And the nice robustness feature probably is this one. Whenever this energy through delta 2 is bounded, you're sure that the state will eventually go to 0. Okay, so well, zero gas, I already used the statement, but it means that the input-free system is gas. I had this characterization also valid for time delay system, that if the system is zero gas, it's the same as having a Lyapunov-Krasovsky functional, which is coercive, which dissipates in terms of the whole history norm, but modulo an input term that is multiplied by xt. So this is not very good in practice because this L of xt can be very big. And so there is no reason why this should be ever negative. But anyway, if I rescale this Lyapunov function by a function pi of class k, I can reshape it into some function w, which has a dissipation that looks really like integral ISS. Now alpha is just a positive definite function, and gamma is a class k infinity function. So if you look too quickly, it looks like from zero gas, you get something that looks a lot like integral ISS. But what you have to keep in mind is that this pi is not guaranteed to be a class k infinity function, meaning that this w here might not be a proper radially unbounded function. So that's why you don't conclude integral ISS. So anyway, this is just a delay extension of this result by David Angeli and co-authors to time delay system. It still works.
So just question, it's a zero gas or zero U gas characterization here?
It's a zero U gas, sorry, absolutely. You start with a KL estimate.
Okay.
Yeah, sorry. So same here, zero U gas. In order to show integral ISS, it's actually enough to show that the input-free system is uniformly globally asymptotically stable, and that in addition, you get an LKF whose derivative might be positive, but not so much with respect to U, meaning that it's bounded by eta of U of t. If you have these two ingredients, then you get integral ISS, and this is a result by Lin and Wang in 2018 in the context of time delay system, and also the original result, which was referred to as zero output dissipativity, was from Angeli and co-authors in 2000 in finite dimension. So based on this, we have this Lyapunov characterization of integral ISS for time delay system. And essentially it says that whatever dissipation is fine for integral ISS. Let me say it like this, meaning a history-wise, so alpha here is just a positive definite. History-wise, with coercive Lyapunov function, just history-wise, LKF-wise, point-wise, KL-wise, as I told you, it's interesting for functions of the form logarithm of 1 plus w. All of them ensure integral ISS. Okay, so essentially the conjecture we have for ISS can be considered as a solve for integral ISS. Okay, so this is the idea of the proof, but maybe, I mean, I can come back to it if you want, but maybe I will go to the conclusion. Before concluding, I want really to send my warmest thanks to all my co-authors on this topic, Yasin Chitur, Johan Göksu in Turkey, Yason, Epifine, my current PhD student, Paolo Mazon here, my former PhD student, Jakub Orlowski, Pier Domenico Pepe, Mario Sigalotti, Yuan Wang. So thank you a lot, guys. It was a pleasure to collaborate with you. And also to some other colleagues with whom I have not yet published, but we have intense discussion on this topic, like Luca Brivadis here in my lab, Hernan Naimovic, Yabaida, Jose Luis Mansilla Aguilar, Andrei, Alexandre Seren, Fabian Weir. So thank you. It's all very interesting to discuss with you. And maybe a word to conclude. So what I've shown you is an overview of the ISS theory for time delay systems. So I believe it showed you that this is a mature topic with a lot of available tools, and yet several open questions. And according to me, yeah, they would deserve some more investigation, whether the forward completeness implies bounded reachable set property, whether gas is necessarily uniform for time delay system, and whether exponential stability or ISS can be ensured using only a pointwise dissipation. I want to mention finally that the survey I told you about at the beginning of the talk covers some other topic that I have not discussed today, like solutions-based characterization of ISS, input to output stability property, IOS, and feedback interconnection, cascade interconnection that I have not mentioned today. That's all for me. I thank you all for your attention. Thank you.